under non-standard conditions. So if you're asked for the Gibbs free energy and it's standardized simply means that all of the concentrations are going to be in 1 molar concentrations. So whatever concentrations, aqueous concentrations you would have would be in 1 molar. And every gas you would have would be at 1 atmosphere. And if you have those conditions, you really don't need to do much. You look up every one of those on a table. There's a table for every compound, and you can find the standard entropy or Gibbs free energy for it. And I wrote this down. So this particular example, I've got silver chromate is breaking apart into silver ions and chromate ions. And so I wrote down the standard free energies for each of these compounds. And all you would do is multiply 2 times the 77.1 and add it to the chromate, which is negative 728.8. And then when you get that, you are going to then subtract the reactants, which would be 1 mole times negative 641.8. So that would be it. And in fact, that's the first step you're going to do for this one as well, because if you have a non-standard conditions, there is a formula that you're going to use, but it includes the standard free energy. So you're going to need it either way. So when I wrote it down, this is going to be the standard reaction free energy is simply going to be the products. Remember, that's the moles times the number, the free energy number. Add them together and then subtract the reactants. So I used this to find the standard free energy, and I found it as 68.2 kilojoules. Now that's the standard free energy of this reaction. And you need it in the formula that we're going to use in a second. So the formula that you're going to use for non-standard conditions is delta G. So this is free energy but not standard. The little 0 there in the superscript means the standard free energy. So this is just normal free energy, non-standard conditions, is the standard free energy plus the product of the gas constant, and this is the 1 in joules per Kelvin, so 8.3 I think, times the Kelvin temperature times the natural log of your reaction quotient. Okay, so this is complicated in a lot of different ways. The reaction quotient, remember, is like K. K is at equilibrium. Q is any time that it's not at equilibrium. So if it's not equilibrium, your K is not K yet. Okay, it's Q. But you find it just like you found your K. So I look at the balanced equation, I look at the products, and I see that I've got 2 moles of silver nitrate, or silver ions. So it's going to be the molarity of the silver ions squared times the molarity of the chromate ion. Okay, and that's going to be to the first power because its coefficient is to the 1. Then I'm going to subtract, or I'm going to divide by the reactants, but the reactants in this case is solid. So I ignore it. So the Q would be just like K. Solve for the K, or solve for Q, and then fill everything out. Okay, so I've got the free energy in kilojoules. But if you recognize that my gas constant is in joules per Kelvin, when everything cancels, I'll be in joules here. So I've got 68.2 kilojoules. And then I've got negative 7,360 joules. So I have to make sure they're both in kilojoules. Please don't fall into that trap. That would be so easy to fall into and get a wrong answer. So when you combine them, they're asking here to do it in the nearest kilojoule. Okay, so you want it in kilojoules. So it was 68 or 60.8 something, and so it rounded up to 61 kilojoules. Okay, so using a formula, pretty simple, but lots of parts to it. So I hope this helps.